All right, guys, so I think I'm ready to go here. Welcome to the lab. I am getting prepared to do part one, where we're going to go ahead and figure out the molar extinction coefficient, or the molar absorptivity for the iron thiocyanate that we're going to be making. So we're going to start by calibrating our spectrometer here. There's some chem wipes so we can wipe on the outside. Okay, so remember to calibrate this machine. We're just going to put in a sample of DI water. And essentially what we're doing is we're letting it know where the zero is, right? If it's zero concentration, then the absorption should be zero. All right, and we're calibrated. So then the next thing we're going to do, on the instructions, it actually says to put in a wavelength of 450 nanometers. This machine will actually determine that wavelength automatically. So I'm not totally sure that it'll come up with 450 nanometers when we run it, but we'll find out here in a second. So for this experiment, I know in the instructions it says to use 0.2 molar iron nitrate. I don't have any 0.2, I do have some 0.1, and it's a pain in the butt to make. So we're gonna go and use 0.1. So instead of being 1,000 to 1, it's 500 to 1 is the ratio, but it really should work just fine. Okay, so we've got our two solutions there. And according to the first sample that we're supposed to make up, the first standard solution should be 2 milliliters of the potassium thiocyanate. And for our purposes today, it's going to be accurate enough to use some graduated cylinders. So well, let's see. Let's go here. Okay. So there's our 2 milliliters of potassium thiocyanate. And you can see there's a kind of a red color on the test tube, but when I actually mix these two, or sorry, not the test tube, the graduated cylinder there, but when I actually mix these two, you should see another red color start to appear. It's kind of a reddy orange color in the solution itself. Alright, and so we'll just mix this up here. This is a really fast equilibrium, so we don't have to worry about waiting too long to run the experiment. And then we'll go ahead and transfer that into another cuvette. In addition to figuring out the absorbance, we also need to know the concentration of this sample. I will show you in another video a little bit later how we do that calculation. All right, so you can see there, we get an absorbance curve. You'll notice that the peak is actually up here in the ultraviolet region, but we're going to use this, it's advising us to use the wavelength here at 450 nanometers. You'll notice that we still get pretty significant absorbance there at 450. Anything beyond that, the absorbance starts to go pretty far down. Okay, so we're going to tell this system that we want to use 450 nanometers. Okay, and then we're going to go to our concentration. Well, all right, so now we're on the point where we're going to do Beer's law here. So it's telling us right here that we're using the 450 nanometer wavelength. Okay, and we're going to tell it the first concentration. And again, we'll go over how to calculate the initial concentration here, because that is a calculation that you will have to do to complete the packet. But the initial concentration for this first sample is 0.00004. Okay, so we're going to enter that there. All right, that's actually the solution that's currently in the device, and so we'll just hit record and it'll tell us the absorbance. and the initial absorbance is 0.65. It's jumping around a little bit, but 0.65, 0.66. Okay. And so then we're going to do that for each of the other samples, and then we'll come back and I'll show you how to do, or how we're going to go about doing part 2. Okay. All right, so I finished doing all of the absorbances for the standard set of solutions. I plotted the concentration versus the absorbance and got a nice linear graph with an R-squared of 0.994. And I've got an equation there that doesn't seem to go through 0, but I'm going to use that equation ultimately to calculate the absorbance, or rather to use the absorbance to calculate the concentration in part 2 of the lab. Okay. I did end up having to make one modification. The sensor was getting overwhelmed at 450 nanometers, so I upped the wavelength to 490 nanometers, and that ended up giving us a really nice straight line for our graph. So we're going to run this at 490 nanometers instead of 450. Okay. All right, so in part 2 of the lab, the biggest difference is that we're going to be changing up the concentrations. So you can see there I've got 2 bottles. These are both 0.002 molar. So at this point, we're not using Le Chatelier's principle to influence where equilibrium lies. In the first part, right, we were driving equilibrium to the right by using a huge excess of iron ion. Now we're not trying to do that. We actually want to know what the equilibrium constant is for this reaction. So we've got 2 equal concentrations. We're going to make up the 5 different test solutions that are described in your packet. And then we're going to measure the absorbance, and that will tell us the concentration of the iron thiocyanate in that particular test solution. And then we can use that to find equilibrium. So I'll demonstrate one here on camera, and then I'll give you the rest of the data in a hard copy. Okay. So the first test solution number 1, calls for 5 milliliters of 0.002 iron nitrate. Okay, so that's the source of our iron ion. Okay, so we need 5 milliliters there. Okay. We need 4 milliliters of water, DI water. So I'm just going to use a squirt bottle here, make it easy. Okay. And then 1 milliliter of the potassium thiocyanate here. And once I add that potassium thiocyanate, hopefully we see a little bit of color showing up in the test tube. That's the iron thiocyanate actually forming. All right. Not a lot of color to it, but definitely a little bit. Hopefully that's enough to absorb. So I didn't have any more of the small ones, so I can't use my thumb anymore, so I'm just going to stick a clean pipette in there. Mix it up a little bit. Make sure that it gets to equilibrium that way. And then we'll see what we measure here when we go to do the absorbance. In hindsight, for the sake of the video, it might have been better to start with the higher concentration so you could see that color, but it'll be the same color as we saw in the standard solutions, so it shouldn't matter too much. And there's just a little bit of color to it, so hopefully that's enough to actually absorb. All right, it's pretty low, 0.02 for our first sample, but this should be the one that is the least concentrated. We'll do that for the other 4 test solutions, and then in a subsequent video I will show you how to do the calculations. Okay.